Hi, and welcome to our 16th video on atomic structure from Allen High School. We're going to be looking at some AP questions, and let's jump right in. It says, answer the following questions regarding light and its interactions. Now, we've been focusing on the interactions with atoms, but we're going to be looking at molecules as well, and really not much of a molecule, but focusing in on a bond here. Now, the first part gives us a wavelength and it asks us for frequency. Go ahead and start writing symbols by those numbers. Don't just circle the numbers, put the symbol by it. And I think if you do that, you will be led to our formula, which in this case, the speed of light is the wavelength times the frequency, or lambda nu. Now, it gives us wavelength in nanometers. I think it's very helpful to memorize the speed of light in nanometers per second. And that's going to equal our wavelength, 495 nanometers, times our frequency. And if we solve that for frequency, our frequency is therefore equal to 6.06. And I expect you to double check my math. You know that my mind gets ahead of my mouth, which gets ahead of my hand. So please help me out with that, and I can at least put comments for the sake of others. So that's part one. Now, part two asks us for the energy of the photon. Now, there's two ways we can do this, because we have a formula for energy and frequency that is given. Energy is h nu, and it's implied but rarely written that we're talking about the energy of a single photon when we are talking about that. But we could also do a little bit of algebra and come up with this equation. This is not given. I happen to like that, and I'll often use that. But in this case, since I already have frequency, it's a few less keystrokes into my calculator. So I'm going to ignore that one, and we're going to jump right into the other. So energy is 6.63 times 10 to the minus 34th. Planck's constant is given in joule seconds. And I'm going to multiply that by my frequency, which was 6.06 times 10 to the 14th seconds to the minus 1. And you notice those cancel, and I'm left with joules. So the energy of my photon, if you did the mathematics for that, would be 4.02 times 10 to the minus 19th joules. Now, I'm going to put in, as we lead into part three, an explicit denominator here that I think is helpful. And most people won't write it down, but I like to. That's joules for one photon. Well, how am I going to get from the world of photons into the world of bonds? In other words, I want my photons to cancel, and I want bonds. Well, I hope it's logical that one bond, one photon, breaks one bond. And so that's a 1-to-1 ratio. Probably didn't need to show that, but I'm hoping that that will help you understand my direction. Now, this question asks me for moles in the denominator. That's moles to the minus 1. Unfortunately, those little prefixes didn't, or superscripts did not come out very well when it loaded up here. So I have eliminated photons. Now I have bonds. I want to eliminate bonds and go to moles. And I've mentioned many times that the most common use of Avogadro's number seems to be to change something in a denominator. So now I get rid of bonds, and if I stopped my math, I'd have joules per mole. But it didn't ask me to stop my math. It asked me for kilojoules. So I have to go to kilojoules and get rid of joules. Now, too many of you are trying to do this in your head, and you're moving your denominator the wrong way. So you might as well set this up. It does not take very much time. And I end up with an answer in kilojoules per mole. And one of the reasons that that is so valuable is because that's how these are reported in tables. Bond energies are reported as 242 kilojoules per mole. If you look that up in the back of your book, that's what you'll get. And it's always listed as a positive because it's assumed that you, as the brilliant chemist that you are, and quit laughing because you freaking know you're brilliant chemists, that it's positive if we're breaking bonds because it requires energy to break that force of attraction, and it would be negative if we are forming bonds, if energy is released when we form that force of attraction. Okay, so that's the first part of this question. Now let's go on to the next part. And it shifts gears just a little bit, and it's talking about transitions from energy levels. We're using that Bohr model that you did in WebAssign, questions 16, 17, or 15, 16, and 17 on WebAssign. We're talking about the hydrogen atom, and remember that Z squared is equal to 1. Now, AP gives the hydrogen formula. That's left out, but that's going to help us as we get into the very last part of this question. All right. Now, the first part of this question asks us to indicate and justify whether we're dealing with emission or absorption. Now, you could do a calculation to prove that. You could calculate delta E, and if delta E is negative, it's an emission. If delta E is positive, it's an absorption. But it may be in a part where you don't have access to a calculator. So I'm going to go ahead and justify it using statements. We are going from a high value of N in our transition to a low value of N, which means we are going from a high energy state to a low energy state. And when you go from high energy to low energy, you're typically relaxing, and you kick back and relax. And that's an emission process. So emission, and I'm going to run into the white here, so ION, emission process. Okay? So that's how you could justify that. Or you could do the calculation that we're about to do in just a minute. Now, the next part asks us to calculate the wavelength. Well, in order to calculate the wavelength, we actually need to calculate that delta E. So you actually could have done part 2 before you did part 1. And if you didn't know part 1, you could have done part 2 anyway to get those points, and it might have led you to part 1. So always read every part of the questions. So part 2, I need delta E first. And delta E in chemistry, a delta in with one exception, is going to be your final minus your initial. And that I'm going to use the formula given to us by AP. It's on your formula chart. This over N squared, which is 4, minus 2.178. Some of you can tell right away that we could do some factoring and maybe simplify our plugging and chugging into our calculators, and we can indeed do that. So that would be the formula that we need to calculate our change in energy. And if you do that algebra, we are going to get 4.84. So my change of energy is equal to negative, because it's an emission, and your algebra should give you that negative, 4.84 times 10 to the minus 19th joules. Now, we need to move from the world of the electron into the world of electromagnetic radiation. And it's not logical to have a negative energy for a photon. So what we do is we take, to get the energy of that individual photon, we have to take the absolute value of that difference. And so that's going to be a positive 4.84 times 10 to the minus 19th joules. Now, I'm going to go directly to wavelength. You could do it in 2 steps if you want. You could go from energy to frequency to wavelength in 2 steps. I like to go in 1 step. I don't know, it seems to me that it takes less writing. 6.63 times 10 to the minus 34th. For the speed of light, since it's asking for this in nanometers, I'm going to use nanometers for my C, and you can see how handy that is to memorize that. The more you memorize, the less you have to look up. The less you have to look up, the faster you can go. The faster you can go, the better you can problem solve, and the more your points you'll rack up, and the more you will be proving to us just how brilliant you are. Now, if you did this algebra, you're going to get 411 nanometers. So we're nearly done with this question, but there's one more point that it asks us to make. In this case, it's asking us about the helium ion compared to the hydrogen atom. And it makes a truth statement. It's telling you this. It's not asking you to predict it, although you certainly could calculate it, and we did calculate it in the notes. It's telling us that that change in energy for the helium ion, +1 ion, the helium +1 ion has only one electron. And it's telling us that that change in energy is greater than what it would be for the hydrogen atom. Now, we have to prove why that's true. And there's a couple of ways you could do that. You could just use logic, and you have to write more words than I'm going to spend time on this video, but I'll give you a good idea, and you can kind of fill in some of the pretty language. But remember, you don't need complete sentences to convince somebody you know what they're talking about. This is not an English essay. Now, remember that when we talk about properties, we're always talking about, to justify, you've got to talk about electron-electron repulsion, or electron nucleus, proton, or positive charge on the nucleus, attraction. Now, in this case, they have the same number of electrons. So that's not going to be a factor. We must be addressing this. So our nuclear charge on helium is +2. Our nuclear charge on hydrogen is +1. That means that energy level 2 is going to be closer to the nucleus for helium, as will 6, but the difference is still going to be bigger. And that's because the change is going to be by z squared, not just z. So that means our change, that delta E, is going to be different. Now that's one way. The other way, it's always handy, in my opinion, to throw down a mathematical formula. Maybe not always, but most of the time. Throw down a nice little mathematical formula. And this is the one that you're given, right? That's for hydrogen over n squared. But we talked about in class, and we did calculations with, in fact, you caught that because I had that 9 squared when it should have been 9. This is z squared. So now you can point to this as part of your justification. Look it's times z squared. And so it's times z squared. I have 2 squared as opposed to 1 squared. The difference in energy will be greater. And so that's how you could be justifying those types of questions. And I do expect you to put a few more words in it than I did, but honestly, not many. You'll need some words to wrap up all of these symbols here in a little bit clearer language. So, good luck, and hopefully you're able to do your AP homework based on this. But for now, this is signing off.